Next topic is scavenging in two-stroke cycle engines. So it's called two-stroke engine because for one complete cycle, this engine only need to have one crank rotation, so 360 degree, and the piston only move from top center to bottom center and then back again to top center to complete the cycle. So in two-stroke cycle engines, every downward stroke of the piston is a power stroke. So it is from top center until the point where the transfer port is open. So to achieve this behavior, the burnt gas have to be replaced by fresh charge while the piston moves through its bottom center position. So you can see the schematic on the right figure. So initially the exhaust port will open, okay, and then the the burnt gas will exit the cylinder chamber because of the pressure difference. So the pressure inside the cylinder is pretty high, and then the one inside the exhaust port, then this burnt gas will exit the cylinder chamber. The period during which the product of combustion are exhausted from the cylinder and the fresh charge enter. So this is the gas exchange period, or it's called scavenging process, begins at the time that the exhaust port is first exposed. So look at again on the schematic on the right feature. So this is the time where the exhaust port open, and then the piston continue its movement toward bottom center. So bottom center will be somewhere here, okay? So, and then on the next occurrence, the transfer port, so this is the port where the fresh mixture entering the cylinder. So the transfer port open and the fresh mixture will enter the cylinder chamber at the time the exhaust gas is expelled from the cylinder chamber. So these two processes occurs simultaneously. So that's why we have to have a good scavenging process to make sure that the entering of this fresh mixture help scavenge the exhaust gas from the cylinder chamber. There are several different categories of two-stroke cycle scavenging, and the location and the orientation of the scavenging ports control the scavenging process, and the most common arrangements can be seen in this feature. So in this feature we have three different scavenging configuration. Starting from the left, it's called cross scavenging. As you can see here that the fresh mixture enter from the left. Okay, so we have fresh mixture entering from this side, and then we have a special feature of the piston top surface that will deflect this fresh mixture up. Okay, will deflect it up instead of going straight to the right. Okay, the purpose of deflecting this fresh mixture is to maximize the scavenging process so that more burnt gas is expelled from the cylinder chamber. And it's called cross because the location of the transfer port from the fresh mixture is about 180 degree from the location of the exhaust port. So this is the exhaust port flow. So this is the exhaust port. The second category here is called loop scavenging. So in this case, the location of transfer port is about 90 degree from the location of the exhaust port, and the system is designed in such a way that the fresh mixture enter the cylinder chamber and then follow the loop direction here, so that the scavenging process is maximized. So once again, the idea behind having this configuration is to maximize the scavenging process of the burnt gas and finally improving the volumetric efficiency of this engine. And then the third configuration, it's called Uniflow Scavenge configuration. So in this case, we have multiple transfer port, okay? And then the flow exiting the transfer port and then enter the chamber is designed in such a way that they can have a certain flow pattern. It can be kind of swirl flow that is intended to maximize the scavenging process, and the burn gas exit this engine from the top side. And you can see there it has also it exhaust valve, okay? In this feature we have two exhaust valve, okay? So this is an example of the three different scavenging process commonly used in a two-stroke engine. And this is the common porting arrangement, so it's actually similar to the fresh picture, but we have a different view on this feature. So this is the common porting arrangement that go with cross scavenge. So this is A here, so this is cross scavenging, and then B here is for loop scavenging. So in A you can see there that the fresh mixture entering from the left, and then the exhaust exiting from the right side of the chamber. And then B here we have a loop scavenging, okay? So there are several different configuration even on this one type of the scavenging. And then C here is a Uniflow scavenging, so the fresh mixture enter the cylinder chamber from different direction, okay? And then the exhaust gas exit the engine from the cylinder head side. Next one is looking at the scavenging process principle. So this feature is showing the gas exchange process for this two-stroke engine. So A here is showing the valve and port timing and pressure diagram. So we can start by looking at point B here, where the first port is open, okay, and then the pressure decreases, okay, and then maybe several degrees after the exhaust port open, the transfer port will also open. So this is the transfer port where air coming from the intake system is entering the cylinder chamber. So in this case, we use a compressor to have a higher pressure to enable scavenging process. And then this is a piston, so that's move to the left and right. So the cylinder axis is in the horizontal direction. And then on the B here we have a pressure, and then scavenging port open area, okay? So this one is the pressure profile, and then this is the scavenging open area, and this one is for the exhaust. So you can see in here B here begins before L. So B is the initial point of the exhaust port opening, and then several degrees after that the transfer port open, okay? So it is at this point, okay, this point. So you can see in here in two-stroke engine they have a decent overlap period. So therefore we need to have a very good scavenging process to make sure that maximum burn gas is expelled from the cylinder chamber while the fresh mixture is entering the chamber. Because of this unique scavenging process in a two-stroke engine, some of the fuel is also expelled along with the burn gas. This is because we cannot make a perfect scavenging process with, let's say, efficiency of 100%. So this is one of the reasons why a two-stroke engine has a lower fuel conversion efficiency compared to the 4-stroke engine. In a 2-stroke engine, usually the fresh mixture is pressurized when entering the cylinder chamber. So this is intended to improve the performance of the engine during the scavenging process. And this air or mixture pressurizing can be conducted with a different method. This figure is showing common methods of pressurizing the fresh charge in a 2-stroke cycle engine. On the left side, it's called crankcase compression. So in this case, the fresh mixture enters the crankcase first before it is admitted to the cylinder chamber. And this crankcase gets pressurized when the piston moves down from TDC to PDC. And then on the second one in the middle, it's called crankcase compression with a root blower. So in this case, we use a rotary machine with the blower type to increase the mixture pressure entering the cylinder chamber. And I'm assuming that you already learned this different rotary machine in fluid mechanic or different class. So it's called blower because the direction of the mixture entering the machine is the same as the direction of the mixture exiting the machine. And then the method number 3 on the right side here, it's called centrifugal compressor. So it's called centrifugal because the direction of the mixture entrance is perpendicular to the direction of the mixture exit. So all of these 3 methods are intended to increase the mixture pressure when entering the 2-stroke engine. This figure is showing a configuration of the piston. So they call this a piston deflector. So as I mentioned to you in the previous slide, it was intended to improve the scavenging process. So as you can see in here, we have a unique feature of the piston. Let me put a red color here. So this is the unique of the piston. So because of this unique feature in the piston, the fresh mixture entering the cylinder chamber, okay, and then it's get deflected and then it's moved up instead of, let's say, straightforward to the right. So with this flow deflection, it will maximize the scavenging process of the exhaust gas. And then how do we quantify the scavenging process performance in a 2-stroke engine? There are several parameters that are used to quantify the scavenging process. One parameter here is called the delivery ratio. Okay, so this parameter is formulated as the ratio of mass of delivered air per cycle divided by a reference mass. This reference mass is defined as displaced volume, so displaced volume from the 2-stroke engine, times ambient air density. Okay, and then ambient air density is determined at atmospheric condition or at the intake condition. Okay, same thing as the volumetric efficiency definition in a 4-stroke engine. The second parameter, it's called the trapping efficiency. So it's theta TR. So this is the ratio of mass of delivered air or mixture. So we have 2 options here at the air. So it's mean if it is a diesel 2-stroke engine, then we only have air, and might be plus recycled exhaust gas. Okay. And if it is a spark ignition 2-stroke engine, so and then we have PFI, then what is entering the engine is the mixture of air and fuel, and might be plus recycled exhaust gas. So back again to the trapping efficiency. This is the ratio of mass of delivered air or mixture retained, okay, divided by mass of delivered air or mixture. We have word written here, as I mentioned to you, that some of the fresh mixture is also exiting the engine along with the burn gas. Okay, so this trapping efficiency indicates what fraction of the air or mixture supplied to the cylinder that is retained in the cylinder. The next parameter is the scavenging efficiency, or theta SC. This is the ratio of the mass of delivered air or mixture retained divided by mass of trapped cylinder charge. Okay, so the scavenging efficiency indicates to what extent the residual gas in the cylinder have been replaced by fresh air. Okay. And then we have another parameter which is called the purity of the charge, beta. This is the ratio of mass of air trapped in the cylinder charge over mass of trapped cylinder charge. Okay, so just to see the purity. So this is the degree of dilution. So the degree of dilution with burn gas. And then the last parameter here is called the charging efficiency. Okay, it's theta CH. So this is the ratio of mass of delivered air retained over the displaced volume times ambient density. So this indicates how efficiently the cylinder volume has been filled with fresh air or mixture.